All right, so greetings. Welcome to week three, and today we'll be solving three questions. So let's get right into it. So first question is: LTI system is governed by y double dot of t plus 12y dot of t plus 20y of t equals to u dot of t plus 4 into u of t. So we have to find what is the dominant pole, the coefficient that multiplies the exponential term corresponding to this dominant pole in its unit step response, and the steady state value of its unit step response. So first, what is the dominant pole? The dominant pole is that pole which is closest to the imaginary axis or closest to the zero or origin. So if we take Laplace transform of the given differential equation, we'll have s square y of s. We'll also substitute zero initial condition here. So 12 into s into y of s plus 20 into y of s is equal to u dot of t. So s into u of s plus 4 into u of s. Taking the y of s and u of s term common, we'll get s square plus 12s plus 20 into y of s is equals to s plus 4 u of s. So let's call our transfer function to be g of s, which is y of s over u of s. So uh, the transfer function becomes s plus 4 by s square plus 12s plus 20. So let's factorize this transfer function s plus 4, and if I have factor as 2 and 10. So in part A we are asked what is the dominant pole. So the dominant pole is the one which is closer to the imaginary axis or origin. So poles here are minus 10 and minus 2, and the zeros of this transfer function are minus 4. So if we draw the imaginary axis and the real axis, this is the origin. So the one which is closer to 0 or imaginary axis is the dominant pole. This is answer for A. Now we want to take its unit step response. So U of s is 1 over s. So y of s is g of s into u of s. So we have s plus 4 in the numerator, s from 1 over s plus 2, and s plus 10. So we will have to work with partial fractions here. So let's say a over s plus b over s plus 2 plus c over s plus 10. Now if we take this expression and multiply by s over both the sides. So this s would get uh, this s would get cancelled, this s would get cancelled, so we will be left with a, and s will get multiplied to this term and this term. So when we substitute s equals to 0, this term would go to 0, this term would also go to 0, and we'll be left with a on this side. So a is equals to, as I said, this s would get cancelled, and so what we are doing is we are multiplying by s on both sides and substituting s is equals to 0. So when we substitute 0, 0 plus 4 is 4, and in the denominator 0 plus 2 is 2, and 0 plus 10 is 10. So this is 4 over 20, that is 1 over 5. Now we'll multiply by s plus 2 and substitute s equals to minus 2. So similarly, this b term will be preserved, sorry, the b would be preserved, this term would go to 0 and this term would go to 0. So we'll get an expression for b. So in the numerator, let's put s equals to minus 2. Numerator is 2, s is minus 2, and s plus 10 would be 8. So this is minus 1 over 8. Now similarly, we'll multiply by s plus 10 and substitute s equals to minus 10. So this time the c term would be preserved, everything else would go to 0. So the numerator would be minus 6, denominator is minus 10, and s plus 2, so minus 8, which would become minus 3 over 40. So y of s for the unit step response would be 1 over 5 into s minus 1 over 8 s plus 2 minus 3 over 40 s plus 10. Now taking inverse Laplace transform, y of t would be 1 over 5 minus 1 over 8 e power minus 2t minus 3 over 40 e power minus 10t. So this is the dominant pole term, and hence the coefficient of the term corresponding to the dominant pole is minus 1 over 8. And since we have already found out what y of t is, the steady state value of the output is limit t tending to infinity y of t, which would be 1 over 5, then e power minus 2t as t tends to infinity would go to 0, and e power minus 10t as t tends to infinity would go to 0 again. So we'll be left with 1 over 5. So this would be the answer for C part, and this would be answer for the P part. Now coming to the second question, the governing equation of a first order linear time invariant system with time delay is y dot t plus 2 of yt equals to u of t minus 0.2. So here we have delay of 0.2, that is the input given at 0.2 before the current time instance would get implemented at the given time instance. So if we take the Laplace transform, we'll get s into y of s plus 2 into y of s equal to, since there is delay of 0.2, we'll have e power minus 0.2 into s into u of s. So if we want to write the transfer function corresponding to the given LTI system, this would be e power minus 0.2 into s over s plus 2. So what is Faraday's approximation? Say the delay is given by the say the delay in the system is minus td or td. So we write the term e power minus tds like e power minus tds by 2 over e power tds by 2. Now we can go on and take the series expansion. So we have 1 minus td into s by 2 and other higher order terms, and in the denominator it's 1 plus td into s by 2 plus other higher order terms. So what we are doing is we are taking the exponential term and uh, creating it into a term with fraction with the numerator polynomial and the denominator polynomial. So since we are only interested in first order approximation, this would be approximated as 1 minus tds by 2 and 1 plus tds by 2. So the approximate transfer function, say g1 of s, would be, we'll have 1 over s plus 2, and from the pad approximation we will have 1 minus 0.1 s and 1 plus 0.1 s. So we can multiply by 10 in the numerator and denominator just to get 10 minus s in the numerator and s plus 2 and s plus 10 in the denominator. So this is first order pad approximation of g of s. So coming to the next question, here we have a system whose Planck transfer function is given by 5 over s square minus 2s, and the controller transfer function is s plus 1. So we want to find open loop and closed loop transfer functions considering negative unity feedback and comment on the closed loop stability. So let's first draw a closed loop block diagram. we have the controller C of S and the plant P of S, and in the closed loop system we get a reference signal R of S, and we are looking at a negative feedback, say H of S. So the output of the plant is Y of S and the control input is U of S. The controller takes in the error between the reference value and the feedback W of S. So this error, let us call that as E of S. Now this negative sign here signifies that we are working with a negative feedback. When we are saying unity feedback, that means H of S is equals to 1. So what is the closed loop transfer function? We can write this simply as R of S, the closed loop transfer function of the system, which results in Y of S. So we are interested in this closed loop transfer function. So let's slowly start writing from the output shown here. So Y of S is equals to P of S into U of S. This U of S is coming from the controller. So U of S is essentially C of S into E of S. The error term E of S is reference minus the feedback, and the feedback is function of the output and the feedback transfer function H of S. So this would become R of S minus Y of S into H of S. So now let us take this E of S and plug in here to find U of S, and then we will get U of S, which we can plug it in here. So the U of S term would become C of S into R of S minus Y of S H of S. So when we plug it in there, Y of S is written as P of S into C of S. Now what we would do is we can merge this plant and the controller as and call it as G of S. So P of S into C of S would be G of S. And while we are at it, let's open up the bracket. G of S into R of S minus Y of S times G of S H of S. Now if we send this second term on the other side and take Y common, Y of S is, so Y of S in bracket 1 plus G of S into H of S is equals to G of S into R of S. So this is what we said the closed loop transfer function would look like. It will take an input as R of S, which is the reference signal, and its output would be y of s, which is the output signal. So y of s into r of s would be the closed loop transfer function, which is g of s over 1 plus g of s h of s. Now let's take a look at this problem and see what these transfer functions are. P of s is given as 5 over s square minus 2 minus 2s, and C of s is s plus 1. So what would our g of s would become? P of s into C of s. So if we just look at g of s and see its poles, it is one pole is at plus 2 and another one is at 0. So this is in RHP. What is an open loop transfer function? We just break it here and we are interested in W of s over E of s. So we start with E of s. It goes into C to form U and it goes into P to get Y. So W of s would be H of s into P of s into C of s into E of s. So this E of s can be taken in the denominator and we are just left with the product of these three transfer functions. This becomes E of s into C of s into H of s. Since H of s is 1 because of unity feedback, we are left with G of s here. Yeah, so when we are looking at the open loop transfer function here and its poles, we can see that the poles are in unstable. So the open loop system is unstable. So now let us calculate the closed loop transfer function. We'll substitute this g of s here and h of s is already 1. So we'll have 5 in bracket s plus 1 over s square minus 2s whole divided by 1 plus so after we cross multiply this term in the denominator, this term and this term would get cancelled. So we would have s square minus 2s plus 5s plus 5. Now if we look to poles of the closed loop transfer function, this would be minus, say, 1/2 in bracket minus, so we'll have this b minus 3 plus minus under root 3 square is 9 minus 5 into 4 which is 20 minus 3 over 2 plus minus, so we have complex poles with real part in the negative sides, that is left half of the complex plane. So we can say that the closed loop transfer function is a stable system. So with the help of a controller, we were able to stabilize this particular system. Now coming to the fourth question, when the system whose transfer function is 1 over s plus 2 is subjected to a unit step uh, input, the difference between the output and the input asymptotically tends to. So we have been given a system whose transfer function g of s is 1 over s plus 2. We have been told it is given a unit step input. So the difference between the output and the input, that would be y of t minus u of t. So let's call that as difference d of t. So we have been asked what happens to this asymptotically. That means as time tends to infinity, what happens here? So y of s is g of s into u of s. So even before going there, we can look at the poles for this transfer, this function y of s. We'll see the roots of the denominator polynomial are s is equals to 0 and s is equals to minus 2. So we are not in the unstable region. So that is s is not positive, but it is 0. That is, we are just at the border. So let us write y of s as a over s plus b over s plus 2. We'll multiply by s and then put s is equals to 0 to obtain an expression for a, because the b would get multiplied by s, which is 0. So we would have a is equals to 1 over 2, and we'll multiply by s plus 2 and substitute s equals to minus 2. This would result in uh, the a term going to 0, and we can get an expression for b. So that would be 1 over minus 2. So Substituting the values of a and b, we get y of s as this. Now let us take the inverse Laplace transform to obtain an expression for the unit step response. This is 1 by 2 minus 1 by 2 e power minus 2t. So we have been asked what is the difference between output and the input, and so that is t of t is equals to y of t minus u of t. U of t was 1, so 1 half minus 1 over 2 e power minus 2t minus 1. So this will be minus half in bracket 1 plus e power minus 2t. Taking the limit t tending to infinity, since we have asked what happens to this difference d of t asymptotically, we get minus 1 half. So we'll have 1 here, and as t tends to 0, e power minus 2t would be 0. So when the difference between the output and the input asymptotically tends to a constant value minus 1 half. So sometimes let's say that instead of s we have a little bit of delay in our system, as we may never be so sure about it. So this 1 over s would become 1 over s minus epsilon, and then that small value would end up causing some instability in the system. So that was, oh, all right, yeah. So let's come to the next question. What is the settling time of the system with governing equation y dot plus 4 into y of t equals to u of t? So let's first find its transfer function. So taking the Laplace transform, we'll get g of s equal to y of s over u of s. This will be 1 over s plus 4. So this is a first order system, and if we have a first order system of the form, say k over tau s plus 1, then the settling time is given by 4 into tau. So let's divide this by numerator and denominator. We'll divide it by 4. So you'll have 0.25 over 0.25 into s plus 1. So the settling time would be 4 into 0.25, that is 1. Let's assume that the units are in seconds. Oh, yes, so that is all for today's tutorial. We can have some questions if any. All right, so let's quickly go through a recap of question 1. Uh, a LTI system is governed by this equation. We have to find the dominant pole, the coefficient that multiplies the exponent of the term corresponding to dominant pole, and its unit step response. So first, uh, we took the Laplace transform of the governing equation and then substituted zero initial conditions, and after taking the y of s and u of s term common, we came to the transfer function g of s, which is y of s over u of s. After factorizing the denominator polynomial, the pole came at minus 10 and minus 2, and 0 was minus 4. So the dominant pole for an LTI system is the one which is closer to the origin or the imaginary axis. In this case, it is minus 2. What do I mean by a dominant pole? This particular pole would dictate the system response. So if we take individual terms and draw the response coming from the individual term, the resultant response would look very much closer to the dominant pole. Then we took unit step response by substituting u of s equals to 1 over s and obtaining expression for y of s. We applied the partial factors method in order to separate the terms. Then we took inverse Laplace transform, and this is e power minus 2t is the term corresponding to dominant pole, the coefficient of which is 1 over 8. When we take the limit as t tending to infinity, this term would go to 0, this term would also go to 0, and we would be left with 1 over 5. So that is question 1. So any other questions? Yes, sure. So let's take a look at stability of closed loop and open loop. Did you get the derivation for the closed loop transfer function? All right. So this is the final closed loop transfer function. Are we good till here?
Yes, sir.
All right. So mm, let's just see the denominator polynomial as c. So what would be the roots? Minus b plus minus under root b square minus 4ac over 2a. So a here is 1, so denominator becomes just 2, and b is minus 3, so minus 3, and under root this. So if we draw the imaginary axis and the real axis, let me use orange for showing this. So say this is minus 3 by 2, and this is that under root 11 over 2, and this is minus under root 11 over 2 iota. All right. So So the closed loop poles, these are the closed loop poles. So since they are on the left half of the complex plane, uh, these two poles would result in a stable system. So uh, yeah, so since the closed loop poles are on the left half of the complex plane, the closed loop system is stable. But when we look at the poles of the open loop transfer function, that is this 0 and -2. So when we have a pole at 0, the situation becomes slightly tricky. So you would have come across the terms stable system and unstable system. Some people also refer to such kind of systems where one of the pole is at 0 as marginally stable system. So a marginally stable system is uh, something like an integrator. That means if you have a tap which you have opened and you have a bucket, it will keep on filling it, and after some time it will end up overflowing. So in a that is one example of a marginally stable system. However, when we are looking at practice, what we do is we would try to identify the transfer function for a given system. In such a case, uh, if the estimation exercise leads you to believe that one pole is at origin, that means it's in a sense a marginally stable system. The pole in reality can be on either side of the imaginary axis. So sometimes it is outright called as a unstable system when you have once a 0 at the imaginary axis. I hope that answers your question.
Yes, sir.
Yes,
Thank
sir.
you,
Thank
sir.
you, sir.
All right. Any other questions?
That's it
That's
from
it
my
from my
side, sir.
side, sir.
Thank you,
Thank
sir.
you, sir.
All right. Shravan, any questions?
No
No
problem.
problem.
All right. So thank you for joining today's session. Uh, so yeah, do we have any other questions before we wind up today's class? Yes. So where am I uploading videos? Uh, Let me go to YouTube. I think there is some lag in communication from the NPTEL side. So if you can just go to the channel and just keep a tab on it or subscribe, whatever, it will be easy for you.
I actually
Actually
tried
tried
looking for the
looking for the
video and I
video and I
didn't
didn't
find it.
find it.
So
So
that's why I was
Yes.
asking. Yes, sir.
Yeah. So I let me just share a link. I will give you here. So I'll just paste the link in chat box. This is for one of the videos. If you go there and keep a tab on my channel, uh, preferably after every session, I would try to upload it in couple of hours. So by the time you wake up on Tuesday, I can guarantee it will be there on the YouTube channel. Kindly let others know, those who have not joined.
Okay, sir.
okay, sir.
Thank you,
Thank
sir.
you, sir.
Yeah, thank you. So shall we close for today?
Yes, sir.
Yes, sir.
All right. Thank you for joining. See you next week.